Hi, everyone. Good afternoon. Thanks for coming to this talk. Apologies if this is in English, so even if my wife is Russian, but my Russian level is not really good. I can talk about multi-key, but not about technical stuff, so that's just to talk with my children. So just a quick introduction before entering the main topic. So my name is Gulemo Iozia. I'm in February this year joined MSD. For someone coming from North America, probably you will know the company as Merck is one of the top 5 biopharmaceutical company in the world. And in particular, I'm focusing on the manufacturing side because the company is going through a full data and digital journey, and so I've been asked to join the company with my expertise in software engineering, but also data science at the same time to help in this journey. Before MSD, I was part of Optum, which is the tech branch of United Health Group, the bigger healthcare provider in the United States, and before I was in IBM and FAO, which is an agency of the United Nations, just to have a little bit of background of what I did in the past 11 years before joining MSD. Some crazy publisher last year asked me to share my experience on doing deep learning on a JVM-based environment, on a Spark-based environment, and has been published in January. But today I'm not covering talk of the book, but if you're here tomorrow, there is some follow-up of the book in my next talk. I love cooking, so if you want to ask me something about doing the proper Italian pizza after the talk, you're welcome. So unfortunately, I can't prepare anything, but if you have a chance to come to Ireland, you could be my guest. So just a few notes about the company. In Ireland, is present since more than 50 years, so you can see that the stats. And in particular, at the moment, I'm focusing on trying to improve the process of manufacturing the Keytruda, which is an immuno-oncology vaccine, which has been tested against 32 types of cancer successfully. By successful, I mean that the cancer disappears after few treatments. The challenge is to produce as much as needed from our patients, so that's where I focus mostly. I have other projects across Europe because I'm part of MSD EMEA, but that's the main focus and where I'm based so far in North Dublin. So let's enter the main topic. So today you're here for this. This work has been carried out mostly on the company. I was working before joining MSD. So today I couldn't show any source code, but I will talk to you about the implementation, why we reached this. And this is something that I'm assuming you're a smart person and you can reproduce the same on your environment. But at the moment, I'm also trying to convince the company to open source some of this stuff for in 2020. So stay tuned with my blog or through my LinkedIn and Twitter profiles if you want to understand how this would evolve. Just a first quick poll among the participants. How many people use Apache Spark in a production environment? Okay, that's I can say this is a good percentage. Some other talks, there is no one using really Spark. Or at least how many people know what Apache Spark is? Okay, that's good because I just put a single slide about Apache Spark. I want to focus mostly on how to do prediction of performances of Apache Spark, which will be the core topic of the core of this topic, and then a couple of slides about what we did next after we achieved the expected result. And of course, there will be a Q&A session, and please feel free to stop me anytime today and tomorrow, or at the Ask Me corner, of course. So this is the slide about Apache Spark. I'm skipping this because the main topic is pretty long and complex, so I want to spend more time there. This is the reason why I started to do this talk here. I did a similar talk to another conference in July. In March, I was one of the speakers of the DataWorks Summit, presenting the work we did doing distributed deep learning on Apache Spark using some open source frameworks. And what my team, me and my team didn't realize was that we did a proof of concept. We pick up the right technology stack for our use cases, but we didn't think about potential failures using a different tech stack. So during that conference, there were different use cases talking about their experience failing or succeeding with Apache Spark. But this in particular was really interesting to me because I really enjoyed the talk by Pavel, is an engineer at Allegro, Allegro, Poland. He presented how they scaled their Spark infrastructure from 2,000 nodes to a few hundred. And I really like the takeaways of that talk because it was the same philosophy we followed while I was in Optum. So basically, you know, any Spark performance might vary a lot for different reason, and each Spark application is different from another. Also, in the same application, different run, everything could change. And also, some things that developers typically don't do is to try to experiment with the configuration params of your Spark job. I noticed this behavior in a lot of developers where they put a given configuration for a Spark job, not asking themselves, is this the best way to do this? I'm using the proper resources for this job too much. So this is something that really helps on maximizing performances and reducing hardware usage in Apache Spark cluster. So what, first of all, we need to stay on the same page on the definition of failure when we talk about Apache Spark. Looking at the Oxford English Dictionary, I found 3 definitions of a failure: lack of success, the neglect or omission of expected or required action, or the action or state of not functioning. These are the root definition of failure, but if you are talking about air conditioning system or Apache Spark clusters or car engine, failure could have different meanings. So I'm going to present now 3 examples of what are to me failures in an Apache Spark environment, so that you could better understand what's the message of the rest of the talk. So this is the first example. Imagine you have a Spark application running, it stops, and you find something like this in your log file. Definitely, this is a case of failure because something bad happened in the memory management for this Spark job. So I think that in this case, everyone agrees that this is a failure, just in case there is someone that thinks that this is not a failure. You never know. So definitely, I can see a couple of the Oxford definition applying to this use case. Is a lack of success, definitely, and the action or state are not functioning. This is the second example. Imagine you have your Spark application running. Everything seems fine at the end. You look at the Spark web UI, and you see that the status for all of the tasks of this stage are a success. So cool, everything seems fine. But if you look deeper, you look at the shuffled right side column, you can see that there is an imbalanced amount of data across the different tasks of the same stage. You can see that for the stage number 0, there are more than 100 megabytes of shuffled writes. There is a small amount of data, is 4.5 about for the task number 1, and negligible amount of data or shuffled write data for 3 and 4, and basically tasks for from 4 to 7 are doing nothing. But you are this way keeping busy some resources for nothing. So this is a clear example. It's very simple where you are misusing the resources of your Spark cluster, and this is something that should be prevented at development time. I don't have in this slide the source code example, but basically the developer should have think of something, a better repartition of the data before starting the calculation in order to skip this situation. So definitely to me, this is a lack of failure, and this is the, coming back to the Oxford dictionary definition, this applies on this case because someone didn't do the proper action before putting this into production. This is a third example that I've seen a lot of time. You're running Spark applications. The Spark applications are taking longer than expected to complete the execution that at the end is successful in terms of the results. And typically what people do are adding more nodes to the cluster or adding more physical resources to each node. It could be RAM or it could be CPUs. This doesn't solve the problem because sometimes it's true. Probably I observed a case 1 year ago of some guys that were trying to run a Spark application with a small cluster of 3 nodes on 2 or 3 terabytes of data. That's the case where you have to increase nodes or physical resources. But in most cases, you're just shifting the problem or skipping the problem because the problem is in production. This would work for the next run, but you don't know what could happen. And anyway, you're spending money to do this. So to me, this is a failure because, again, is the omission of expected or required action by developers or whoever is responsible for infrastructure, anyway, is a lack of success. And this is will be the main focus of the solution I'm going to present today, which is based on someone call it AI Ops. It's a fancy name, but at the end it uses optimal experimental design, machine learning, and lately deep learning. This is one of the things we did. I'm going pretty fast about this. This was much more something to provide the facilities for developers operation. Anytime there was a new failure in the logs of the Spark cluster infrastructure. I'm not going through the detail of this. At the end, it's simple data science. So the guys used deep learning for J to implement a model, a neural network, to get all of the Spark logs and other logs from the environment and try to identify patterns of potential failures and build some templates that could then provide a better visualization to whoever have to consume those error messages. So basically, we moved from a situation like the one on the left to the one on the right. That's not the final UI, but just to give an idea. Imagine yourself as a developer or someone in the operations, and it's a better experience to have something like that with some potential suggestion rather than examine a stack trace with in Spark. Typically have 5 levels of depth among other information. So this is not going to the details of this because it's, as I mentioned before, it's not rocket science, but the next one, this is the more important point. I want to pass the message to think about out of the box often when you have problems or when you simply want to make things better with a proactive approach. When people often need to think about improving Spark performances or do prediction about the performances of Spark application, they don't do nothing or they just guess. They run the Spark job, and to me it's equivalent to like reading tarots for this, so it has the same business value at the end. What we did was, these were the objectives of the teams in my area. Of course, predict in order to improve performance of Spark job and minimize resource utilization, because in a model of pay-per usage, that was a significant achievement. Shift problems from production to the left at development and testing time, not discover things after you deliver this to the final customers of the patients, and of course satisfy the SLA for the specific project those Spark applications belong to. In order to do this, we didn't try to reinvent the wheel. I found this, just before this is important, some background information first. We used to manage the Spark cluster in the pre-production and production environments, which were based on OpenShift origin. Basically, it's Kubernetes with a layer on top, flavor of Red Hat OpenShift. But we try to use as much as possible Kubernetes features and not using specific OpenShift, because then we want to move these things on a different environment, supporting Kubernetes, not just for our on-prem or our private cloud environments. The proof of concept started in middle 2017, before Spark 2.3. This is important because Spark 2.3 is the first major release supporting Kubernetes as a cluster manager. So we try to do this, deploy and manage Spark and Kubernetes before this feature was available. So this is an extra challenge we had. Of course, we upgraded in 2018 to Spark 2.3. And the Spark cluster management has been done initially, integrating this open source project by Red Analytics called O5. So basically it's a facility to scale up and down dynamically Spark clusters. This was a perfect fit for us for the first iteration. Then the guys had to fork the project and implement some specific feature for our use case. So at the end, we didn't rely on the official source code of O5, but there was an Optum-based branch which is still closed source. And all the use cases we had were related to Spark jobs implemented in Java, Scala, and no Python use cases. I believe that the same solution would work for mostly for Python-based Spark job, but there are some significant differences that I'm not going to cover today, so I will refer mostly to Scala and Java Spark job. So how many people are familiar with Scala or Java? Okay, many people with Python? Okay, so unfortunately today I don't have anything for Python, but my talk tomorrow will be mostly Python-based, so I have something for everyone. And the data we used to manage, we moved away from Hadoop and have, depending on the specific use case, specific project, we have data in Cassandra, in MySQL. Some customers have data in Amazon S3. Of course, the storage system could add extra complexity that will affect the performance of your Spark job. Consider, for example, Cassandra. If you don't choose the proper data modeling in Cassandra, this will screw up the performance of your Spark job. Even if your code is perfect, you think about internal Spark, but if there is a bad data modeling, the performance will be affected. And I'm not talking about this because this requires another probably 6, 8 extra hours for the talks, focusing mostly on the overall Spark application and their internals. So in order to, this is the challenges that if you work with Spark, probably you already know about them. We need to apply some machine learning model and lately some deep learning model to address this, to predict performances. The problem is that we didn't have enough data or meaningful data because Spark jobs don't run repeatedly on the same data set. If you run an application now, if you run the same tomorrow, we have all of the data coming from these runs, but they couldn't be compared. It's not apple to apple. Some of the Spark jobs we have were related to training some machine learning model or do just a parameter optimization. So in this case, it could be probably just a single run, so you don't have enough data to do this. Last but not least, Spark is a complex ecosystem. I just narrowed the scope here on what we were using, but Spark is not restricted to this. So there are different libraries for different things, for graph analysis, Spark SQL, machine learning, other stuff. We had in the infrastructure different submission methods, and this influenced the performance as well. Of course, the infrastructure were very flexible, but had this contribution on performances. Having Kubernetes, we have something to auto-scale Spark cluster. We had the Airflow to schedule jobs for also other teams. So forgot to mention that in this infrastructure, we have to manage Spark application implemented by different teams, not just by my team. So we didn't own the code of those applications. They were part of the overall continuous delivery pipelines. As soon as there was a change on our corporate GitHub, we start to build the application, run all of the tests, move this to the pre-production environment, and then assess performance, and then send notification to them. So you can imagine you have different teams with a different skill set, different background. Not always you have the best implementation possible for a Spark application, which is a very complex word. Because we didn't want to reinvent the wheel, I found this research paper from the AMP lab at the Berkeley University. Just for those people who don't know, this group is the group, the lab to which Matej Zakaria and other guys who implemented Spark belong to, so they know Spark very well. And the challenge they had was that they had this Spark infrastructure on Amazon using EC2 machines, and they have some problems in terms of costs. They want to understand if the performance of the Spark job were really optimized for that infrastructure, understand if they are using the infrastructure in the proper way. So they did this paper. They suggested an end-to-end linear model that takes just small samples of data to predict the Spark application performances, which is our case because we really had small data to train the model. And it follows an optimal experimental design to achieve this. This is a technique when you have to few data or you have a huge data set, but you want to choose small significant data points to train your model. And this, of course, is implementation suggested by the AMP lab, has a low overhead on the overall infrastructure, which translates also in reducing or not impacting the costs. There were some cons because we couldn't adapt this as it was to our infrastructure, because they validated this against the EC2 instances only. In our case, the infrastructure was different, and so we have to revalidate everything again for our use case. They had only Spark application based on the MLlib Spark library, so they are doing some training of machine learning models. We are not using MLlib. I suggest you not to use it. It's in maintenance mode now, but it's not the best way if you want to do machine learning or deep learning with Apache Spark. Please use other libraries. And it was some sort of black box approach. Let's go back to this last point in a few minutes. I want to show you how this system works and how we changed it for our specific use case. So this is the overall flow of Ernest is the name of the project, named after Ernest Hemingway. I don't know why, so but anyway, that's the name. So the first part of the flow is the experimental design implementation. You have to provide very few input data to this part, which is the minimum and maximum number of partitions you want to use, because this system is based on running the Apache Spark application, not on the full data set. Imagine the company here was a company processing a trillion claims in the healthcare space per year. Combine this data with other data from healthcare providers, members, government institutions. You can imagine you can run for testing Spark application on the full data set. This way you just choose a small portion of the full data set to run this, so there is a very low overhead. And you specify the minimum and maximum number of pods. I'm talking here about pods because in our Kubernetes infrastructure, we have a single Spark node and a single pod. And how many cores and also RAM you had for each pod. When the experimental design phase starts, this produces a small list of configurations, and then you have to run your Spark application on your cluster using those configurations. Remember, it's just for each one of for each run there is you use just a small part of the full data set. During these cycles, you collect data, which is a small training data set that you will use then to train your machine learning model and do prediction about the performances of the same Spark application on different Spark cluster. Of course, we integrated this in our continuous delivery pipeline, so anytime there was a change in the Spark application code, this was part of starting again with experimental design and the model training and the prediction. So this was always updated for each change in the source code for those applications. And of course, you train the model for each application. But anyway, at the end, you have a low overhead, so you can do this in a large organization like the one I was working for. So if your organization is smaller, this would be far way better. And I put some numbers here on how this works. Imagine you have this simple situation. You want to run the experimental design phase, and you provide the minimum number of partition and maximum number of partition of the overall data set, which in this case had 256 partitions. Specify the minimum number, maximum number of pods to consider in your infrastructure, in this case between 1 and 8, and how many cores available for each pod. When the experimental phase completes the execution, it's very fast, and it produces a list like this. So you have for each configuration a score. So it means it's producing only those scores that only those configurations that would be meaningful to run the application and collect the data to train your machine learning model. And then you start cycling, running the application with these configurations only, that in this case are 7. At the end of the execution, you collect the data, and I cut the list here. So basically, you have the overall execution time for each configuration, and this will be the training set of your machine learning model. Forgot to mention one thing before. The Ernest model, the guys at AmpLab identified some pattern of execution for each Spark application, whatever the application is. So there is a collection phase of the the data. There is an aggregation phase, and then there is the one that produces the result. So we have to verify that this is true not only for Spark job to train machine learning model, but for other things, because we had Spark application for link analysis, for data movement, data transformation, whatever. So this is still useful. And then with this data, you train the model. The machine learning model could be, the paper is pretty open to it. So you could use just simple model like a non-linear least square sequence, or whatever machine learning model you want to put, you want to implement for this specific use case, at least considering this as a black box approach. And then when the model completes training, you start to make predictions, and this is the result. So it basically, the model is saying you that for different configuration, different number of nodes, that will be the overall execution time for your application. So it means that you don't need to run the Spark jobs for any possible configuration. This is the result of your prediction. So why is important this, even if it's some sort of black box approach? Because from this, I can get a lot of useful insight. Look, for example, for running with 4 pods only, there is a predicted execution time of 7.5 seconds. Moving to 8, the prediction is that you have a reduction of the execution time of about 35%. So it's good. So people what do normally say, okay, I moved from 4 nodes to 8, so if I move to 16, I will have better performances, which is not true. Because you are introducing for this specific use case more shuffle. So moving to 16, you will have a worse execution time as compared with 8. So the model is telling you that for this use case, please stop on 8, because that will be the execution time if you run this job on the full data set. The accuracy we received for this model was initially around 88%, then moved to 90-91, which was good anyway, because we moved from having nothing to something pretty accurate, and so we reduced the waste of hardware for our Spark cluster, and using Oshinko, it was really easy to scale the cluster for that specific usage, and destroy the cluster as soon as the execution finished anyway. There are also some other use cases we had where running the prediction, we had prediction time of comparable across different configurations. So that means that there was something bad in the Spark code, and I have an example in a couple of minutes about this. So anyway, this is a black box approach, but gives you a lot of useful information. We want to move further anyway to fine-grain this prediction, and we added an extra layer to this tech stack. So we introduced Spark Measure, which is another open source project maintained by Luca Canali at the CERN in Geneva. They use this in production with their data, which are pretty huge data sets. And basically, this project uses the same Spark listener mechanism of Spark. So the same way the executor sends data back to the driver, and that are used by the event log, by the Spark Web UI, of if enabled by the history server. So they didn't reinvent the wheel, but they produced some way to use this listener to get the metrics you need and store this on some other data storage. By default, Spark Measure support at the moment only file system, physical file system, HDFS, and Prometheus. We use Prometheus because Prometheus was part of our infrastructure. Prometheus is a time series and monitoring system which is open source. And there are 3 ways to collect this data in Spark Measure. You can instrument your code, but this was not suitable for us because we didn't own the source code of most of the Spark jobs running in the infrastructure. We could use the flight recording mode, so it means you run in Spark jobs and then collect information on the fly and send them to the proper sync. Or it's possible anyway to do this from a notebook in Scala on Python. If you go to the Spark Measure GitHub repository, there are some links to some notebooks that run on Databricks, on Google Colab, any other notebook engine, and you can check yourself for this. The way we did was to use this in flight recorder mode, and this is the way that we changed the infrastructure. So we didn't touch the original Ernest part. At the moment we run the configuration, application with those configuration suggested by the experimental design phase, we start to collect magic with Spark, the Spark measure, and then with the support of putting them on Prometheus, with the support of a data science team, they implemented the neural network model to crunch this data and start to do prediction that we have to merge with the other prediction about time there. So this way we have a prediction about the overall execution time, which was very accurate, and also some information about what's going on inside the Spark job. And this is an example of outcome of this. Coming back at the error shown at the beginning, there is an unbalanced partition of, for the task of this stage. And this is something that you can quickly check with Spark Measure and combine this data. You can send a notification back to the development team responsible for that Spark job. And after the change is committed, again, the pipeline runs. And this is what you could observe in UI. You can see that for the same Spark application, the same stage, all of the tasks have comparable execution time, and also very small shuffle write data sites comparable each one. So it means that you're not wasting physical resources in your Spark cluster. This is just an example, but you can have a lot of information about getting this metric to Spark Measure. Forgot to mention that one important feature of Spark Measure is that you have two different levels of details for the metrics you can collect, at the stage level or at task level. Of course, at task level is much more fine-grained, but this has a little bit overhead if you try to run this on a production environment on a huge data set. It wasn't a problem for us to run in pre-production at the task level, so we have more information. And the bad news is for Python developers. If you try to train a model or run something with Spark using Python, unfortunately, Spark Measure doesn't handle whatever happens outside the JVM environment. So this is a limitation we had running some deep learning training using deep learning for J, because most part of the stuff is not in the heap memory, but is off heap, and Spark Measure doesn't cover whatever happens in the Spark there, or the same if it happens in the Python engine. So that's the only limitation so far for Spark Measure. Don't know if there is some way in the future they will change this. But the experimental design and the machine learning model, the overall Ernest process applies to whatever. If you use PySpark, you can do the same, because there is no reference to the internals of Spark. After this successful experience, we want to move further. And as I mentioned before, after a Powell talk, we want to create something, some way that the Spark application could, during at execution time, understand if their performances were good and auto-tune themselves. In order to do this, we have to move to reinforcement learning. So you're asking why there is Pacman there, because it is the best way if you don't know what reinforcement learning is to understand the concept. So basically, is another specialization of in our case, deep learning, because we use neural networks as well as part of reinforcement learning. So basically, you have an environment where there is an agent. In this case, is the Pacman character. The agent has some rules. So in this case, has to eat all of the pellets and try to skip the ghost, because they could kill it. There could be some. The agents could reach some states. For example, where anytime he reaches some energy pellets, If you're familiar with Pac-Man, I'm assuming so, you know that for a few seconds the Pac-Man can kill ghosts. But this could create a situation where the agent thinks that is satisfied about this state and stay there rather than completing the maze. So there could be some sort of policy of punishment or awarding the agents if reaches the proper state. And the implementation we start to do before I left the organization is to typically use a neural network and some other integrated with some other machine learning algorithm. Anyway, we use deep learning for J, Apache Spark for the training, the upper parameter optimization, validation of the neural network. Don't know the state of this work because then I left the organization. At the moment, we are in my current organization, we are not at the level we could think about this because there are other problems to address before as we're moving from a traditional approach to manufacturing to a new one based on data and based on machine learning and deep learning or whatever would come next, moving toward one day probably artificial intelligence. So that was the last slide. This is just for people interested in the book. It's available everywhere. You can buy a book online. It could be Amazon or Packet Publishing, also in torrent. So the chart in torrents is very popular over there. So if you download on torrent, that's fine. Oh, here this slide is quite messy and big screen. So there are all the links about deep learning for J, Spark Measure, the Ernst paper. So if you're interested in, I will share this probably in my blog or on LinkedIn next because I don't know why it's showing really, really messy. So this would be interesting. Okay, that's all for today. So my goal, I hope that this would help you to, in your specific infrastructure, to think outside the box, whatever you use. If you use Apache Spark or something else, don't stop, say, okay, the performances are good, but think always, oh, there is some way to do things better. So that's important. This is the right mindset, and having a proactive approach to things. I consider that what we were doing is something in the DevOps space, but at the end, this was a benefit for the final users, which in our case were the patients applying for Optum plans or following some specific medical treatment through Optum. So that's also should be a personal commitment to do better things, thinking at the outcome for your patients or customer, whatever is your business. So that's all for today. Please feel free to contact me anyway, and we have some time yet for Q&A. And thanks again. Okay. There's a question over there. Going to check Slido, just in case there is someone. Okay.
Hello.
Hi.
Thank you for the interesting presentation.
Thank you.
Of course, I understand the drawbacks of EC2, so it's like money for nothing. But what's wrong with ML-lib for Spark?
Basically, the main issue with ML-lib is that it's fully implemented in Java, or Java Scala, I don't remember. So it runs entirely in the JVM. If you use this in particular for complex machine learning models, so if you try to implement your neural networks by yourself using the ML-lib API, you have to choose between accuracy and performance. So you have to pick up one. So performances could be excellent, but if you look at the accuracy of the model when you validate it or move to production, you will see that probably things could go better, or vice versa. Probably you reach the better accuracy for the model, but performances could be slower. So there are, when I was in Barcelona in March, there were a lot of use cases trying to do this with ML-lib. That's why it went in maintenance mode. So if you upgrade next to new version of Spark, you probably you wouldn't see any extra feature or fixes next. And also during the event, there was Alden Karau, which is the project maintainer of Spark, that addressed people. So please use something else. There are plenty of choices anyway. If you work with Java or Scala, of course, if you work in Python, you have other libraries that are better than MLlib.
Yes, so could you please recommend probably us some
Yeah,
tips?
depending if you, it depends on the programming language
Python.
and also the specific use case. So if you do something in Java, Scala, or any JVM language, for deep learning, the best is deep learning for J, because the core implementation is in C++ or in CUDA if you use GPUs. But from a development perspective, you just write Java, Scala, Kotlin code, so you don't have to care about the underlying things.
Yep.
And also, it's very high level. So if you are never done something with, you're not a data scientist or never done something with deep learning, it's a very high level, the best start, and also the perfect balance between performance and accuracy. There are other frameworks for deep learning. We did some comparison. There is one from Intel called Big DL, but it's tailored much more for their hardware. So if you run on Intel hardware, it's good. If you have something else, forget about it.
Yeah, I mean, in case of JVM, it's pretty much easy. So everything, Spark itself is JVM. So.
Yeah.
But if we need to run Python.
In Python, the best frameworks for ML and DL to me are Keras and TensorFlow, depending on the entry level of the people. So if there are people with excellent software engineering skills, but very low data science, Keras is the best. Anyway, Keras is becoming the high-level API of TensorFlow. I will cover this tomorrow. And TensorFlow is good in particular because it's not just for the machine learning piece, but to cover the end-to-end pipeline. The challenge is that if in your organization there is not enough funding to have GPUs, you will need to do something distributed with Spark, with TensorFlow, Keras, or PyTorch or whatever. That could be a challenge, and I'm going to cover this tomorrow. There is a way to put these things together working properly on Spark.
Okay, thank you.
Welcome. So, any other question? Let me check. No? Okay, so if there are no other questions, feel free to reach me. There is another question here on the first line.
I want to say respect for the DL4J. Very like. Do you have some problem with new architecture, Neuralink with DL4J? As I know, this framework doesn't have architectural attention, for example, or maybe you can tell about some problem. Minus and plus DL4J with compare for TensorFlow, for example. So for yes, it's my question.
Okay, basically, yeah, good question. So because in terms of integrating on an existing infrastructure, so there are the pros are that anyway, typically the infrastructure is mostly based on something running of the JVM. So if you think about not only Spark, but also Kafka, Elasticsearch, the streams data collector, so it means that all of the best practices you typically do for any JVM-based language applies over there, and also the entry point for people not very skilled with data science. The cons could be about the latest version of the JDK, because the latest version of DL4J works fine with Java 8 and 9, and I think it doesn't work with the latest version, which probably at the moment is the 10% of the production infrastructure in the world. That could be a challenge. With the ML flow, the pro could be that you have an end-to-end infrastructure to train, evaluate your models. But if you use this end-to-end, it's fine. If you want to integrate with something else into the infrastructure, which was also our case because the company was too big that I had a lot of licenses with Confluent for Kafka, for example, or Elasticsearch. I think that would be a challenge because in MLflow at the moment, probably things will change in a few months. They think that people use this end-to-end and don't integrate with some other things that you could have in-house. So that's probably the good balance. So it depends on your specific use case. So if you don't need to use anything else, MLflow, it's a good option. It wasn't available when we started this in 2017, was in an early stage, but now it's more stable than then. Don't know if this answers your question.
Yes, thanks.
Да, все, друзья, спасибо большое. Аплодисменты для нашего спикера. Подарочек приноси.